Okay, Math at Work 10. This is going to be your starting lesson on our Chapter 7 Trigonometry unit. Okay, so we've already been dealing with a lot of work with right triangles so far when we've been doing Chapter 6 and looking at the Pythagorean theorem. Okay, and that's been all dealing with trying to find missing side lengths. Okay, what we're going to be getting into with Chapter 7 is a closer look at trigonometry where we not only use Pythagorean theorem to find missing side lengths, but what happens if you don't have two sides and you instead know information about one side and an angle? How can we figure that out? Okay, so that's essentially what we're going to be getting into and finishing up our online learning phase is with this Chapter 7. What we start with, though, today is a lesson on similar triangles and scale diagrams, okay? Because that kind of comes into play in terms of when we talk about things being in proportion to each other, and no matter what the angle is, if things are the same angle, they're same ratios, okay? And we're going to get into that. So today we're just going to focus on similar shapes, right? And being able to kind of make scale diagrams, okay? So let's get into that. All right, so like I said, this is Chapter 7. So again, just kind of talking about this, we've already been dealing with those right triangles. Now we're going to be taking a look at some other, focusing some other stuff, okay? So again, similar shapes, and we've already kind of talked about them a little bit when we talked about the Pythagorean triples, right? So we talked about one of the most common Pythagorean triples being the 3, 4, 5 triangle, and you could determine if something was a Pythagorean triple if it was a multiple of that 3, 4, 5, right? So if you took all the sides, if you had a 3, 4, 5 triangle, and you multiplied all the sides by 2, you get a 6, 8, 10, right? Because 3 times 2 is 6, 4 times 2 is 8, and 5 times 2 is 10, right? Or if you took all the sides and you multiplied them all by 3 and got a 9, 12, 15, 9, 12, 15 triangle, right? And that was a way you could tell if something was going to be a right triangle, okay, is if it fit that Pythagorean triple scale. Okay, and that's kind of what we're going to be talking about now, is that those triangles are all considered similar triangles because they have the same proportions. Okay, so you'll hear us talk about a couple things. One, you'll hear us talk about a polygon, right, which we already know. It's just any type of two-dimensional closed figure, right? So it's like got all sides that kind of make up an enclosed shape. Okay, and then when we talk about similar figures, that's the key thing for this lesson, is that similar figures, they have the same shape, but they're just a different size, right? It's the exact same type of shape, it's just been made bigger, or it's been made smaller, or it's just been flipped around, or flipped upside down, something along those lines, okay? Things to know about similar figures is that they have equal corresponding angles, okay? So the angle in between particular sides doesn't change, right? You're just changing the lengths. Okay, and so notice how the corresponding angles have to be equal, but the corresponding sides just have to be proportional, right? And what that means is that all of the sides are that much bigger than the original shape, or all the sides are that much smaller. Okay, so it's not like you're just lengthening one side. If you're doubling one side, you're doubling all the sides. Or if you're cutting one side in half, you're cutting all the sides in half, okay? So when we talk about something called like corresponding sides, okay? So if you've got similar shapes, right, the corresponding sides have to have the same relative position, right? So they have to connect to similar angles, all right? So if you've got so like looking at these shapes here, we see that B and E, right, these are corresponding angles, right, because they're both the right angle. You see here that with this little circle, that indicates that these angles are the same, meaning that these are corresponding angles as well, okay? And again, C and F, they've got that little line there, that also indicates that these are the same angle, okay? So again, if these are similar, right, these two triangles are similar because they have all the exact same corresponding angles, okay? And then what we would look at here is looking at their corresponding side lengths, okay? So they have to match with the same. So notice how this side length here, AB, it goes from angle A to angle B. Okay, the circle angle and then the right angle. So the corresponding side length would be this one, DE, because it also goes from that circle angle to the right angle. Okay, the side length BC here, that goes from the right angle to the half circle angle, I guess, right? would correspond here to EF because it also connects those same two corresponding angles. And then here, because these were right angles, it's easier to talk about AC, right? That's the hypotenuse, right? Because it's directly across from angle B, the right angle. So that would correspond to DF, right? Also the hypotenuse, okay? So when we talk about corresponding sides, it's the sides of those shapes that match their corresponding angles. Okay, so I mean, this one is relatively obvious, so you can see what's happening, but sometimes like a shape gets rotated or flipped upside down, and you just kind of need to either try and redraw it or visualize it in a way that they actually do match up, and you can see what the corresponding sides are. Okay, so when you're trying to determine whether or not two given shapes are similar or not, you do need to actually check a few things, right? So one, first, take a look at the appearance, right? Does it look like the overall shape is the same, right? Obviously, a rectangle can't be a similar shape as a triangle, right? And there are lots of different types of triangles, right? A right triangle can't be a similar shape as some, just a non-right triangle. Of course, it wouldn't work, okay? But not all right triangles are considered similar. Okay, so does the shape appear pretty much the same and in proportion to each other, just like enlarged or shrunken down? Okay, so that's kind of the visual check, right? That's not a confirmation, but it's a good little visual. Yeah, they look kind of the same. Let's continue with the exploration, or no way are these the same. There's no point to even continue checking, okay? We then have to look at the other conditions of, being similar. So you also have to check that all the corresponding check your corresponding angles being equal here, right? So take a look at the way the shape is rearranged and say, okay, well, these ones match with these, right? So this angle corresponds with this one, so if there's a right angle in there, match those up, okay? And then you'll have to check to see that all of those angles are in fact equal, okay? So if all the angles are equal, then there's a chance that you do in fact have similar triangles or similar shapes, okay? But, you have to double check and do your due diligence, and also check that you can look at the corresponding sides, okay? So I should actually change that, right? But this is true if they're triangles, right? If their corresponding angles are the same in a triangle, then you know that those shapes are similar. That's not necessarily true for, let's say, rectangles, because all rectangles are going to have corresponding angles equal because they're all 90 degrees, okay? So I'll actually go in and make an edit there and do that for triangles. Okay. Now, if you don't have any information about the angles, you can instead look at the corresponding sides, right? Or even if it is, okay, you've got that check mark of yes, your corresponding angles are equal. Now it's time to check the side lengths. Okay, so your side lengths, your corresponding side lengths won't be equal in similar triangles or similar shapes, but they'll be in the same proportion, right? Which means if one of our side lengths has been multiplied by 3 to get the new one, then all of the sides of the original shape have to be multiplied by 3 as well. Okay, and then if they're not, right, if one's multiplied by 3 but the other one's only multiplied by 2, then it's not the same proportions and you do not have a similar shape. Okay, so here's some examples. So these two shapes here, they would be considered similar shapes, okay? We know this one, like if we do an inspection, yep, it looks like it's approximately the same shape, right? It's just been kind of shrunken down a little bit. If we were to kind of, closely look at it, yeah, there's been no rotation, nothing's been flipped. So it's pretty easy to identify that this side length AD corresponds to this one MP. This one along the bottom, AB matches MN. This one here, CB matches ON, and CD matches PO, okay? So it looks like they're fine, but we don't have any information about angles, so we can't check that. However, what we can do is check for proportions of the side lengths. So if all of the side length proportions are the same, then we can confirm that they are similar shapes. So what I would do is I take my corresponding side lengths and I divide them and see what I get. So I take the 6, I divide it by 4, which is what I've done here, and I get an answer of 1.5. Okay, now I do the same thing here. Take this 9, divide it by its corresponding side length of 6, 9 divided by 6, I again get 1.5. Take this side length here, 6, divide it by 4, get 1.5 again. Take this value 3, divide it by 2, 1.5 again. So all of the side lengths, when you do the division, are 1.5, right? So this shape is 1.5 times bigger than this one. So since they all have the same proportion, then we can conclude that they're similar shapes. Okay, we can also look at these ones here in triangles, right? So again, we don't have any information about the angles, but we can look at their side lengths to check for proportionality. Now we can clearly see that both of these triangles are isosceles because two of the sides are the same and then one is different. So when kind of doing that comparison of corresponding side lengths, then these two side lengths that are equal would have to match with these two side lengths here that are also equal. Okay, and then this is the odd one out, so this is the odd one out here. Now, we don't know, maybe this has been kind of flipped around, right, but it wouldn't really matter. So what I'm saying here is that EF could correspond to AB, but it also could correspond to AC if this triangle was just kind of flipped, okay? But again, it doesn't really matter because it'd be the same shape. So again, checking the proportions of the side lengths, 8 divided by 1.6, I get 5. Doing the same thing on this one, 8 divided by 1.6, we get 5. And then here, 5 divided by 1, again, we get 5. So because they all have the same proportion, they are similar shapes, okay? And here's how we would use those angles, okay? So like I said, with the triangle, if all of the angles are the same, then you know you have similar shapes, right? If the corresponding angles are the same, then they have to be the same triangle. Again, that's not true for shapes like rectangles, because obviously they're all 90-degree angles. But for triangles, if they are all, if your corresponding angles are equal, then they're similar triangles, okay? So again, just by looking, yep, they both seem to be right angle triangles. One just seems to be a lot smaller than the other, okay? We can't do the check of all the side lengths in this case because we have all the side lengths of this smaller one, but we only have one on this one. So I can't confirm using side lengths whether or not we have a similar triangle. What we can do instead is look for the angles, right? So based on just appearances, Q and T would be corresponding angles, R and U would be corresponding angles, and P and S would be corresponding angles. So now we just need to make sure that they're all equal. So we can already see that Q is equal to T because they're both 90 degrees, right? And we see that angle R here is 53 degrees, but we don't have angle U. And we can see here that angle S is 37 degrees, but we don't have angle P. Right, so what we would need to do is use that property of triangles where all of the angles in a triangle add up to 180 degrees. So I can figure out what angle P is up here by taking 180 minus 90 minus 53, and I get a value of 37 up here, right? And you can see that I've typed that out for you here, right? So angle P is that 180 minus 90 minus 53 equals 37, okay? So that actually shows, oh yeah, P actually does match with S because they're both 37. Again, I can use that same method to figure out what angle U is here, because all of the angles in a triangle add up to 180 degrees. 180 minus 90 minus 37 equals 53 down here. And again, we see that R is equal to U. So because these triangles, right, have all three of the same equal corresponding angles, then they must be similar triangles. Okay? So let's do a separate example here that's not fully worked out. We'll discuss it, and let's determine if the following shapes are similar or not. So I'm just going to kind of redraw them here on my board. We'll do this one by hand, right? So I've got triangle ABC. There's a right angle there at B. I know that the hypotenuse side length is 10 going from A to C. The bottom side length is 6, and that angle is a 53-degree angle here at C. Okay, then I have a much larger triangle. Still a right triangle though, labeled DEF, right angle there at E. I have side length of 12 along the bottom, I have a side length of 10 along the top, and I have a 50-degree angle here at D. Okay, so let's take a look at how we would determine whether or not these are similar triangles. So starting with this, right, we kind of start with the inspection check. Yep, they look about the same, right? This one just looks bigger, okay? Just by looking at the side length that we have, we could say, okay, well, if this is 6 and this is 12, if these were similar triangles, then that would mean that everything would be doubled, right? So if they were similar, and that's 6 and that's 12, to get from there, you'd have to multiply by 2, which would mean that would have to be true for everything. And you could say, okay, well, if that's true, then if I multiply 10 by 2, right, this should give me a value of 20. Right? Now, if you did that, and then you confirm through Pythagorean theorem, if we tried to do 10 squared plus 12 squared is equal to that hypotenuse squared, right, we would get a value of 100, right? 10 squared is 100, plus the 144 is 244, and then I would square root that, and that's a value of 15.6, which doesn't match the doubling. So if these were similar triangles, this should actually be 15 point, like this is, sorry, if these were similar triangles, this side length should be 20, but it's not, because based on Pythagorean theorem and this right triangle with this side length being 10 and this being 12, this ends up being 15.6, so it wasn't doubled. So you can confirm it that way and say, well, already the proportions are not the same, so they can't be similar triangles. The other thing you could do to conclude that this wasn't a similar triangle is, instead of looking at the side lengths, just look at your angles, right? So you've got corresponding angles here. B is equal to E, right? A is proportional, right? A corresponds to D, and C corresponds to F, okay? We know that these are equal because they both show them that 90 degrees, okay? We know that angle C is 53 degrees. So if these were similar triangles, it would mean that A would need to be 50. So how do we find angle A? Well, again, all the angles in a triangle have to add up to 180 degrees. So to find angle A, we would take 180 degrees minus 90 degrees and then minus 53 degrees and see what we get. So 180 minus 90 minus 53, and we get a value of 37 degrees, which is definitely not 50. Okay, so because those don't match, it's not going to work out, right? And the other thing that you could do is even find angle F by doing the same thing, 180 minus 90 minus 50, and you get that this is a 40-degree angle. Okay, so if these were similar triangles, they'd have all the same angles. They do not, so they are not similar. All right, so that's what's going on there. And again, I've done it mainly with the angles here, and again, since they don't equal, since the corresponding angles are not equal, they're not similar. Okay, that brings us to a topic on scale diagrams. Right now, we've kind of talked about this in a more roundabout way, right? But obviously, scale diagrams are a huge part of things like in architecture and construction, where you want to be able to look at a blueprint and get the actual correct proportions as to what the thing that you're trying to build is supposed to look like. Right, you want it to be proportionally correct with the right angles and the right values, right? But obviously you're not going to be given a diagram that's the same size of the thing that you're building, right? No one can give you a blueprint that's the same size of the building that you're trying to make. It just wouldn't work, okay? But you want to make sure that it's to scale. So you get the realistic idea of the shape of the item being built, but it doesn't need to be the exact same size, right? Because it's not very practical to have a life-size drawing of a house or a building, like I said. Okay, so again, this is where that idea of similar shapes is coming into play, right? You want the same type of shape with all the right angles, right? The exact same angles, but with slightly different, like, actual measurements, right? The measurements are just to scale, and use that making these similar things. So if we look at this example here, okay, so Darlene is a landscaper. She's designing and planting a heritage garden that is an L shape. She needs a scale diagram of the garden layout, and once the client approves the design, she'll be ready to plant. Okay, so she's presenting this diagram to the client saying, here are the proportions, but she's clearly not going to be presenting the client with a drawing that's 10 feet across and 12 feet deep. Okay, but that's the actual dimensions that she has to work with. All right, so the corners are all square, and it's asking us, how can Darlene draw a scale diagram using an appropriate scale? So, like I said, we're not going to be presenting a client with a picture that's 10 by 12 feet, right? However, what we can do is instead say, all right, well, for every, for every 3 feet in a diagram, right, we can say that that's actually just, even a 10-to-1 scale, right? Every 10 feet in the diagram is really just 1 foot on a piece of grid paper, right? So this would just be a 1 foot, this would be 1.2 feet, this would be 0.4 feet, this would be 0.3 feet, right? And then kind of going from there. The scale that you choose is up to you, okay? So you could also make it so that every foot is actually an inch. So if the diagram was 3 inches, right, that would mean, okay, well, if 1 inch is equal to 1 foot, then a 3-inch line here represents 3 feet. And then if that's true, then 10 inches on the diagram represents 10 feet, right? And again, it's going to depend, right? So the example that they use in in the textbook is that Darlene uses 1/4-inch grid paper, and she has a side length of 1 square represents 2 feet. Okay, so you see here we knew that this side length was 3 feet, but she's using every square on the grid is 2 feet. So there's 2, and then 1/2 of 2 is 1, so 2 plus 1 is 3, right? This side length here, right, was a 10 foot. So if every square represents 2 feet, 10 divided by 2 is 5, so we should see 5 squares across here. 1, 2, 3, 4, 5, which we do, okay? Again, this one going down here, that's 12 feet. So if every square represents 2 feet, 12 divided by 2 is 6, so we should see 6 squares going down. 1, 2, 3, 4, 5, 6. Right? Oh, I forgot that I had the diagram right here. Right? Again, this one was 4 feet, so cut that. Right? 1 square represents 2, so we need 2 squares, right? 2, 4. And then everything else matches up this way, right? And you can figure this out, because if you know this whole length here is 12, and this little bit is 3, 12 minus 3 would give you 9, right? So then you'd have 4.5 squares here, 1, 2, 3, 4, and then 1/2. Same thing here, you can figure out this side length. If the whole thing is 10 and this little section is 4, then this would be 6. 6 plus 4 would be 10. So if 1 square is 2 feet, 2, 4, 6, we need 3 squares. You can see there's 1, 2, 3 squares, okay? The next part of the question is, how can Darlene determine if her scale diagram is similar to her original diagram? And again, it's just that concept of checking your side length, right? Checking all your angles and looking at your proportions. So in her diagram, these are all, it was done on grid paper, they're all 90 degrees, right? And we can see that that works. So there's check number 1, right? Checking that all of the angles match, which they do. And then again, it's that idea of using proportional reasoning. Right, so, you know, we knew that these were the dimensions of the garden, right, 10, 12, 4, 9, 6, and 3, and then comparing them, right, like we did before, to the new similar shape, right, say it was 10 goes to 5, 12 goes to 6, 4 goes to 2, 9 to 4.5, 6 to 3, 3 to 1.5, and then check your proportions to see if they all equal the same thing, right, take your longer side, divide it by the smaller one, right, using corresponding sides, so 10 divided by 5 is here. That's 2. 12 divided by 6, also 2, right? 3 divided by 1.5, 2. 9 divided by 4.5, 2, right? 6 divided by 3, 2, right? So we're seeing that, okay, they all equal the same things. So since all of the angles are equal and all the side lengths are proportional, we have similar shapes. All right, so let's look at another application question here, right? Being able to apply similar triangles using the fact that, okay, we've been told that these shapes are similar. How can we use that to find a missing thing? Okay, so here James is building a custom dollhouse for the Hudson family. The dollhouse will be an exact copy of their home. The roof of the home is supported by trusses like those shown below. Each truss measures 12 feet from the edge of the roof to the center. Okay, so we see that from the edge of the roof to the center, that's 12 feet. The height of the truss is 5 feet here. Okay, before he can start his model, James needs to know the length of the top beam. Okay, so this one here. Determine this length. So we'll start with that. And this is just kind of a continuation of our lesson from Pythagorean theorem, right? So, right, we have that this is going to be built straight up, so that's going to be a right angle. We know that that distance going from the edge to the center, okay, that's going to be 12 feet. And we know that the height is 5 feet. And we're basically just solving for the hypotenuse there. Okay, so we can do that just by using Pythagorean theorem. Right, so we can use our a squared plus b squared is equal to c squared. So we can use a and b, right, so 5 squared plus 12 squared is equal to our hypotenuse squared, right, remembering that the c is always the hypotenuse, the one that's directly across from the right angle. So we can square those, so 5 squared is 25, 12 squared is 144, add those together, 25 plus 144, that's 169 is equal to x squared, square root that, and you get an answer of 13. Okay, so we do know that the actual length of that beam is 13 feet. All right, so what's part B asking us to do? So it says here that James plans on using a scale of 1 to 10, in which 1 foot on the diagram represents 10 feet in real life. Determine the lengths of the top beam, bottom beam, and center of the truss to the nearest appropriate unit. Okay, so again, we're using a scale of 1 to 10. Okay, so in our diagram, right, 1 foot on the diagram is going to equal 10 feet in real life. Okay, so this is 12 feet, right, and the scale is 1 to 10. So it's going to have to be a little bit more, right, because 10 feet in real life is 1 foot on the diagram, so it's going to have to be a little bit more than 1. So what we actually do here is we divide by the scale. So what I'm going to do is I'm going to take my bottom, the 12 feet, and I'm going to divide it by 10. And that's going to be 1.2 feet. Okay, I'm going to take this side length, the 5 feet. I'm again going to divide it by 10, and I'm going to get 0.5 feet. And then I'm going to take this side length of 13, so I'm going to take 13 feet, divide it by 10, and I get 1.3 feet. Okay, so my actual diagram, okay, so if I were to edit this, the diagram of the, I guess not the diagram, sorry, they're making, he's making a model, right? In the model of the house, the trusses, this is going to be 1/2 of a foot, right? So that'll end up being 6 inches. This will be 1.3 feet. Sorry, no, that's the 1.2 feet down there on the bottom, and then this will be 1.3 feet. So those are the actual lengths of the model that he'll be using. Okay? All right, so we've got that. And again, those are your answers. Same thing we've just been talking about. So you'll notice here, if we're actually going to figure that out, that was just for the bottom part, right? But if we extend that and we double it, the bottom, the 1.2, we would double it and get 24, so 2.4 would be the actual length there, okay? And then again, you can see that 1/2 a foot can get converted into just 6 inches, and the 1.3 feet, you can say, okay, well, 1 foot's 12 inches, and then 0.3 of a foot is, 4 inches, and go from there. Okay, so that's it now. I want you to try some independent practice there on that I provided, right? Again, the solutions are there, but just kind of checking to see if shapes are similar or not, and then using similarity to find missing side lengths or missing angles, and just kind of go from there. Okay?